So now let's look into a example of a Markov chain, namely birth-death process. So let's look into discrete per process first. It's modeled for a population at a given time. So the number represent pretty much number of people and their probability of P naught of giving birth and the Q1 of dying at the population 1 and the unknown probability of staying at the same at the same same state. So we can define, so pretty much just like PQ Pij, so pretty much 1, so 1 0 become P naught and this become P1, so on and so forth, and then Q1 Q2 going from 2 to where. So formally it will become like these. At steady state, you can imagine it has no influx or influx. So let's look at only I1 naught I plus 1 state. At that state, there's no influx or outflux from any state. So there is influx and outflux, but it has to be equalized in the sense that the flow of probability will equal, meaning at this stage to here, the flow, so from this probability of this state is pi, and then pi I, and then probability of flowing from this state is pi, and pi I plus 1 q I plus 1 flowing out has to be equal. So the flow in equals, so the flow in for this state equals flow out. This is important. We use that. So for the case of all P and Q are equal, Pi and Qi equal, we can define rho P over Q. Thus we have P from here, we have pi plus I plus 1 pi I P over Q, which by definition is rho. So this is like a geometric sequences. Then we have pi I equals pi 0 rho I. If you just, yeah, and then for I'm equal to infinity, we have we know from the conservation of probability state, this should be equal to 0. So pretty much all the terms here, since m equal to infinity, so m equal to infinity, so this become 0, because if rho is less than 1, that means it's stable, because if it's greater than 1, it's just gonna explode. Thus you cannot normalize it, because the Qm will be infinity. So then from this, we know that pi naught is 1 minus rho. So at the initial state, it will have probability of 1 minus rho. Then the expectation value of x naught. So expectation value of however many people we're expecting is pretty much at stage pi naught rho I. So pretty much is a sum of pi I thus is 1. Because it always decay back, because this is a stable. I think this is always a stable equation. As a geometric sum. And this, to a degree, is a Poisson process. For continuous case, you can imagine this is a phone calling center. In a continuous time slice delta t, delta dt, either have a phone call coming in, lambda delta, or the b amount of, this is the factor and this is the constant of probability. B is, so pretty much if you have a B phone line busy, then you have a probability of that is proportional to B, because you can imagine they are going to hang up, have a certain probability of all hang up at a certain time. So it's technically the Poisson process. You can review Poisson's equation on the video I will link. Hopefully I remember. So the learning from the discrete case, we have pretty much pi equals to rho lambda delta qi equal to I mu delta. Mu is a factor. So iPhone number call will be terminated next. So at steady state, we have pi I, pi naught, and then you have to do the multiplication in series, going from 0 to I for pi I of, so pretty much this is Q, this is Pi over Qi equals lambda delta over I mu delta. Delta cancels out. Then we ended up having, this is the constant, so pretty much is lambda mu to the ith power and the I factorial. Since when you can normalize it by the conservation of probability, then we have this. We can put it all together. We have a probability of line the final line being busy is being occupied as such. Thus, if we wanted to be busy at the probability of 1%, meaning there's only 1% of chance that this line will be busy, we need to set, we'll get a number of phone we will require to have phone required to have only 1% time it will nobody can pick up the phone. And I will try to write a Python code. I'll link in the description as well.